4. Actually, this is pretty easy, I feel like.
Okay. I agree. I think. I haven't had a chance to look at this yet, but
Could we just do one to see if I know it for sure, I guess?
all right, sure.
Yeah.
Well, what it means is that the value at C is either a minimum value in that entire interval, or it's a maximum.
Oh, no, I'm talking about 4.
What's that?
4.
Oh, 4. Okay.
Yeah.
Sketch the graph of a function that is continuous on an open interval but has neither an absolute maximum nor an absolute minimum. Okay. I think I can do that. If I have a function between A and B that has no absolute minimum and no absolute maximum, about the tangent function.
Mm-hmm.
That is y equal tan of x. Notice why there's no absolute minimum, because it's infinity.
Could you do like 2 open dots too?
What do you mean?
Like you know how you like the circle dots, but they're not filled in?
Yeah, but oh, yeah, something like this, you mean?
Yeah.
Well, that actually has an absolute maximum there, but
What if it was just a straight line?
let me draw it a little differently. I didn't need to draw it like that. I can draw it the way you want it. In other words, this also works.
Okay.
In other words, I cannot say what the absolute minimum here is, because it certainly isn't A, because we just approach A. We never are at A. So we don't know what value we would put on it if we were to say that's an absolute minimum. Same thing with the maximum. Same thing. Okay. So what next? 5? These are all pretty much similar. I think you can figure out 5. Yes or no?
Let's get your graph says.
That has an absolute maximum. Here. Sorry. Didn't mean to do that. Let me put
Sorry.
it. So let's draw one that satisfies that condition. Has an absolute maximum and a local minimum, but no absolute minimum on 0 to 3, inclusive. Okay, so we need an absolute maximum, a local minimum, but no absolute minimum. Well, I think that satisfies it, does it not? Has an absolute maximum right there. Has a local minimum right there. But no absolute minimum, because this value over here is less than my local minimum. But it's an open circle once again. What's a critical point of a function? If we look at this graph over here on 15, tell me what the critical points are.
Would it be would
Describe.
3 be one of the critical points?
Well,
Oh, that
that one.
one. With P. Would it be local minimums too?
Well, it's where the tangent line is equal to 0.
Oh, okay.
Notice
So it'd be
that at every local minimum or local maximum, the tangent lines are equal to 0.
okay.
Every one of them. You can't have
What if it's
local
horizontal?
minimum or maximum without having a 0 tangent line.
Okay. What if the tangent line's horizontal though?
Yes, exactly. Now, I think that those are the only critical points. If you're looking for maximums and minimums, frequently you have to examine endpoints also, but I don't think those are counted as critical points. In other words, I don't think A and B are critical points.
Mm-hmm.
If they asked you to find the maximum or the minimum in that interval, you would have to check all of the critical points and the end points. Because clearly that's an absolute minimum, A, and B is an absolute maximum. So if you were examining maximums and minimums, you'd want to make sure you check the end points also. I don't think the definition of critical point includes the end points, but I'm not 100% sure.
Okay.
Okay.
And if the tangent line's vertical, that would be a critical point too, or no?
You'd have to, in order to have a vertical tangent line, you'd have to have a non-function.
Well, what about a cube root? Or no, what about a cubic?
No, a cubic has, oh, I see what you're asking here.
Yeah.
If I plot y equal x cubed, there is a point right there which has a 0 slope tangent line, and yet
Would that be
it is neither an absolute minimum, it's neither a relative minimum, let's use their terminology, it's not a local minimum nor is it a local maximum. And yet, whether it's a critical point or not, I don't know. If you do decide that that's a critical point, in other words, usually you're working backwards here. You have the function, you know the first derivative, you can figure out all places where the first derivative is equal to 0, and that's that spot, that spot, that spot, and that spot. Okay? But if you come across a function like this, you also get this spot. And notice that is not a relative minimum. Now, how can you tell the difference?
That makes sense.
You can use either the second derivative test or the first derivative test. First derivative test always works. Second derivative test doesn't tell you anything if it comes out to be 0, which this would. Okay? So how do we know that's not a local minimum or maximum? Because the slopes leading up to that point are plus and the slopes leading out of it are plus. For a point that has a 0 first derivative, for it to be a local minimum or maximum, the slopes have to change. Notice over here on this graph on 15, the slopes go from plus, plus, plus to minus, minus, minus. Down here, they go from minus, minus, minus to plus, plus, plus. In other words, every single local minimum or maximum, the slopes are different signs on either side, but not that function.
Okay.
All right. Now, whether they're called critical points or not, I'm not sure. That's a terminology question. I'm not always completely up to date on terminology. It's one of those things that I don't consider that important. I guess I'm probably wrong. I mean, you have to have certain terminology. You have to know certain terminology. So I don't know whether it's important to know exactly what critical points are. I know that if I'm examining a function, I examine every point where the derivative is equal to 0, and I might also examine the endpoints. Or I might also examine points where the derivative is not defined. In other words, if I have this function here, and I'm trying to find the the relative minimum, which is right there, how do I find that? The derivative isn't defined there. So that's a critical point. So the critical points of a function, actually, there's more than one answer there. It is the points where the first derivative is equal to 0 or not defined. In other words, this function I just drew, the derivative is not defined at that point, we'll call C. And that is a critical point because that can certainly be a relative minimum or even an absolute minimum.
Mm-hmm.
You have to examine cusps and corners as well as where tangent lines are horizontal. So 6 definitely expand that original definition that I said to include places where the derivative is not defined. Let's look at 7. Sketch a graph of a function that has a local maximum value at a point C where f prime of C equals 0.
It's kind of a weird question.
It is. It's pretty easy.
Yeah, because no matter what, it's going to equal 0.
Well,
I mean, it's not necessarily
a maximum. In other words, that's an absolute maximum, but I could have just as easily drawn this function, and there's a local maximum, but it's where the slope of the tangent line is 0. And notice that for local maximums, you have to go plus, plus, plus to minus, minus, minus. You can't go minus, minus, minus to plus, plus, plus. That's the local minimum. This local minimum right there goes minus, 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 comes out plus, plus, plus. So that's how you define whether you're looking at a local minimum or a local maximum without using the second derivative test. Have they taught you the second derivative test yet? For local minimums and maximums?
Wait, what? I'm sorry?
It's pretty easy. What the second derivative test says is if the second derivative, let's see if we want to figure out whether that's a local maximum or minimum. We know the tangent line is 0, okay, but that doesn't tell us whether it's a maximum or a minimum. Well, if we take the second derivative and it is negative, that means it's concave down. If we take the second derivative and it is positive, it means it's concave up. Concave up means local minimum. Concave down means local maximum. Have you learned about concavity yet?
No.
No, it's coming. Next week it's coming. You are right there. Just as a brief thing, that's concave down. That's concave up, concave down, concave up.
Seems pretty easy to me.
Well, yes and no. Sometimes it's not all that clear, and there's always a point where it changes. See that point I just drew?
Yeah.
That's called an inflection point.
That's where the
That's where the concavity changes from up to down or down to up. That's what the inflection point is. And that's where the second derivative is 0. When you find a second derivative of 0, that's an inflection point in the original function.
Oh, yeah.
Okay. I don't want to get too much ahead of you because it looks like we have plenty of material to cover tonight. We've got 5 pages worth. You tell me if I need to go faster. I don't want to spend the whole session on stuff you understand and to the point where we don't get to cover some of the other stuff. Let's skip 8. How do you determine the absolute maximum and minimum of a continuous function on a closed interval? Well, here, sorry, keep doing that. That's an important question, I think. Let's again take that function, and we want to measure it from this point to that point, that closed interval. We'll call that 1, we'll call that 7. Now, how do I determine the absolute maximum and the absolute minimum on this closed interval? 4 places I have to examine. Which 4 are they?
The endpoints
and
the local minimums and maximums.
Right. In other words, the endpoints and wherever you have local minimums. So I have to examine that point, I have to examine that point, and the 2 endpoints. And when I say examine them, I'm examining the y value. Okay, so if that value there is above that, then the endpoint is the absolute minimum. Clearly on my maximum, the endpoint is definitely the absolute maximum. It's not the local maximum there. Okay, you understand that?
Yeah.
Yeah, I don't think 10 we should spend our time on. I think you get this. Whoops. That's my alarm for our 7:30 appointment.
Oh, geez.
I know. I really did believe it was a 7:30. I set an alarm for it. So,
C2 is a local minimum and B is a local, C2 is a absolute minimum and B is an absolute maximum.
good. How about 12?
A is the absolute minimum, C is the absolute maximum.
Actually not. A is not an absolute maximum or minimum.
Wait, why?
Why? Because I can find another point on that graph that's lower. In other words, this point's lower than A.
But you can't really tell.
Yes, you can. That point's lower than A. Here's A. We're looking at that value on the y-axis.
Oh, so there's technically just no absolute minimum.
No absolute minimum.
Okay.
Because it leads into this open circle.
Okay.
Clearly, this value here is less than this one.
Yeah.
But it's not an absolute minimum. I don't know what number I would put on that. It's impossible to put a number on that. That C is definitely an absolute maximum.
Yeah, that's pretty obvious.
Okay. Let me pull up. Let's see. What's our next one? 14. I think that's the next column over. Yeah.
Yeah, it's probably on the next page.
Oh, okay. Let me just go to the next page then.
Oh, one of them was really blurry, so it's the next one.
Oh, so you just did it twice?
Yeah.
That's fine. I'm glad you did that. I don't think I could have read that.
Yeah.
Okay, yeah, here's 14 and 15. So 13, what's it want? What are the directions to 13? They're no longer on my page here.
Oh, it's the same as the previous ones you're doing.
Okay, is there an absolute maximum?
No.
Is there an absolute minimum?
Yes, it's A.
Okay, 14. Is there an absolute maximum?
A. Absolute minimum C.
Okay. Locate or local and absolute. Which local and absolute minimums? All right. These aren't hard. Let's skip these. You know all of these, correct? Am I right?
That's pretty. Yeah, that's easy.
Okay. Unless I see a tough one. About 16. It's the absolute minimum.
A.
Right. And you realize that the minimum they're referring to is the y value, not A. The absolute
I don't know where that is.
The absolute minimum is not A, it's f of A.
Yeah.
Okay, and that's maybe a subtle distinction, but the absolute minimum occurs when x is equal to A, but the value of the absolute minimum is f of A. Is there an absolute maximum?
Yeah, it would be P.
Right, f of P. It would occur when x is equal to P. Sometimes the terminology here is a little strange. Sometimes they look for their answers in terms of x, and sometimes they look for it in terms of y.
Yeah, that's weird.
17 is pretty straightforward, so is 18. Should we look at 19?
Sure.
Okay. So, sketch a graph of a function where f of x equals 0 when x is 1 and 2. So I'm going to put 1 and 2. And I know the first derivative is 0, so the slope of the tangent line is going to be flat at those 2 points. Has an absolute maximum at 4. So we'll put a maximum up there. And has an absolute minimum at 0. So we'll put a minimum down here. And all I got to do is, there's the slope of the tangent line flat. There's a flat tangent line. There you go. In other words, f prime of x equals 0 right there and right there, right? Neither one are absolute maximums or minimums. But that is lower than that. So at 0, I have an absolute minimum. And at 4, I have an absolute maximum. Okay? Next page, I guess. You understand that?
Mm-hmm.
Okay. Next page, the same instructions here, I see. Design a function. I don't know how much time we want to spend on that either. What do you think? Should we do 20 through 22 or should we start on the problems? And the word problems.
Wait, let me see. Fine. Could we do 23?
Sure.
Just like look through. Here, one second. I'll be right back.
Okay.
Wait, against who? How's it going? Oh man. Sorry about that.
That's okay. And notice over here on the right, we do have some optimization problems. You apparently have covered optimization now. I guess you had always covered it. You just haven't covered related rates yet, correct?
No, we've covered related rates.
Oh, yeah, that's right. You hadn't covered optimization last time I talked to you.
No, we haven't. We haven't yet.
Do at least one of those.
Okay.
23 is pretty easy. I'm finding the critical points.
So don't we just take the derivative and set it equal to 0?
Yeah, that's pretty much. If you don't know what to do on a calculus problem, first step, always take the derivative. And I'm only mildly joking. Usually that is the first step on 75% of problems.
Mm-hmm.
Now, what am I going to do to find the critical point?
Set it equal to 0. So f of x equals 0.
Okay, so what's x equal to?
2/3.
Okay. Now, find the critical points on the domain, which is given, and there was no domain given here, so they meant all real numbers. And that's a quadratic. Okay? It's a quadratic that opens which way, up or down?
Be up.
So is that value going to represent a minimum or a maximum?
Minimum.
Is it going to be absolute or just local?
Absolute.
Correct. So that is, oh, it didn't even want that. It wanted just a local maximum or a local minimum or neither. Well, this would also, in other words, absolute minimums are also local minimums. There's only one definition for a local minimum, that there be a point immediately to the left that's higher and a point immediately to the right that's higher.
Mm-hmm.
That's the definition of local minimum. Now, let's look at 24 because there's an interval there. So, and this is, that's a closed interval. Closed intervals, they're never going to be local minimums. It could be absolute minimums. Well, I don't know. Let's take the derivative of that first. What do you get?
It would be 3/8 x squared minus 1/2.
Okay, so we're going to set that equal to 0, which gives us x squared equal 1/2 times 8/3, which means x squared is equal to 8/6, which means x is equal to plus or minus 4 or square root of 8 over square root of 6. The original function is a cubic function, and cubic functions tend to look like that. So you would expect to find two places where the slope of the tangent line was 0, and we did. There's one place, there's another place.
Okay.
One of them is plus root 8 over root 6, and I won't bother rationalizing that or simplifying it, just so you understand. In other words, this is not the answer you would want to give. You would want to rationalize the bottom, so you'd end up with square root of 48 over 6. Square root of 48 is what? 16 divides into that, so that's 4 root 3 over 6, which is 2 root 3 over 3. So that's what root 8 over root 6 is. And it's plus or minus. Now, the plus is going to be the local maximum or minimum, and the minus is going to be the other one. Now, as I was telling you, a really easy way, in other words, once we have these two numbers, if I want to know which one's the maximum and which one's the minimum, take the second derivative. I don't know if you've learned that yet, but let me teach it to you because it's so much easier. What's the second derivative equal to?
That would be 6/8 x, and that's it.
Okay. Now, evaluate that second derivative at these 2 points. Is f double prime of plus 2 root 3 over 3, is that greater than or less than 0?
That would be greater than?
Yeah, in other words, I'm plugging it into the second derivative.
Yeah.
I'm trying to figure out if the second derivative evaluated at that critical point is positive or negative. It's positive. That means it's concave up. That means it's a minimum.
Okay.
That point right there was my 2 root 3 over 3. And then if I examine the other point, then f double prime is negative, right? And when the second derivative is negative, in other words, it's going to be a negative. So I'm going to substitute a negative number in for x. So clearly f double prime of x is going to be negative. Means it's concave down, means it's a maximum. So I haven't drawn this quite right. It should be a negative value over here. But you get the idea? And that is by far the easiest way to determine whether you're looking at a local maximum or a local minimum. Once you've discovered that it is one or the other, the second derivative test is the easier one. Usually because you can take the second derivative pretty quickly and evaluate it pretty quickly. If I have to use the first derivative test, then I got to go and test numbers on either side of this 2 root 3 over 3. In other words, I would test numbers on the left. I would see I have a positive slope. I would test numbers on the right. I would see I was have a negative slope. Since I'm going positive to negative, I know that that is a relative maximum. And when I get to this point over here, the numbers are negative to the left of my value. They're positive to the right. That tells me that is a local minimum.
Okay. Yeah, that makes sense to me.
2 tests. And by far the easier one is the second derivative test. Now, if the second derivative test equals 0, you can't tell what it is. You have to go back and use the first derivative test. So
okay. I feel like at that point it'd be pretty straightforward.
The first derivative test is the fallback. That will always tell you whether it's a local maximum or local minimum.
But I feel like if the derivative equals 0 for your second derivative test, then it should be pretty straightforward, right?
Well, then you apply the first derivative test.
Yeah.
Yeah. If it's equal to 0, the second derivative, it doesn't tell you anything about it. Okay? And you have to go back, and the only thing you can use is the first derivative test. All right. Let's try one of these optimization problems. Is 53 on your list?
53?
We can go back and do more of these if we have time.
Oh, can we just do optimization, though? Because I haven't really gone over that.
53 is an optimization test.
Okay.
In fact, let's do 54. Just because most optimization problems have to do with geometry as much as anything. Okay. Okay. So we have a rectangle. It's a little different, but that's fine. Okay. And we know the area of it. Let's call this A and B. I don't want to call it X and Y because they're giving us a perimeter function that is defined in terms of X and Y. However, they do tell us that the area of this rectangle is 64, right? So area is 64, and that's equal to A times B. With me?
Yeah.
Perimeter, which is the function we're trying to minimize, we're trying to get the smallest possible perimeter, is 2a plus 2b. So the perimeter, they're telling us, has a perimeter of 2x plus 128 over x. Where x is the length of one side of the rectangle. Find the absolute minimum of... All right, this is not as hard as I was making it out to be. Let's not change those variables. Let's just make that x. They said one side of this rectangle is x. Okay? Now, the perimeter is a function. It's 2x plus 128 divided by x. If I take the first derivative of the perimeter function and set it equal to 0, I'm going to find minimums and maximums of that function. For example, I think here, let me do it anyway. 2x plus 128 over x. I want to graph this. I think it'll help with the understanding of it. Two x plus 128 over x. Is that correct?
Yeah.
So that's our function. That's our perimeter function. And notice the two different views here. Notice that this view does not look much like this view. In fact, if you were to look at the top graph, you might be inclined to say that there is no tangent line that is horizontal, right? Looks just like a hyperbolic function. But if we looked at the zoomed out version, which is the lower one, we can see that there is clearly a flat tangent space right here. A flat tangent line there and a flat tangent line there. So if I take the derivative and set it equal to 0, I'm going to find this point and this point on the x-axis.
Okay.
And that'll tell me what measurement of x. Okay, here, let's finish this problem out. Let me minimize that in case we want to look at it again. I got to do this. Hold on. And I want to bring up your page. So, what P prime? What is P prime of x equal to?
So it would be...
Let's write that 2x plus 128x to the minus 1. Now do it.
Okay, so it would be 2 plus negative 256.
No. You're multiplying, start with the exponent. You're multiplying minus 1 by that coefficient.
Oh, yeah, I don't know what I was doing. Minus 128x to the negative second.
Okay. Now that's what we want to hit to be 0. And that'll tell us where on the x-axis that we find our minimums and maximums. So Solve that.
Subtract 2. And then multiply by x squared.
So now we have minus 128 equals minus 2x squared.
And then divide by 2. And then take the
64 equals x squared. X equals what?
8.
Plus or minus 8.
Oh.
And
yeah,
it's important because there are 2 points. And we need to figure out which one is a maximum and which one's a minimum, or do we? Yeah, they're looking to minimize the perimeter. So we know that that minimum comes, well, at one of those values, either minus 8 or plus 8. If we go back and we look at Wolfram alpha, we can certainly tell which one it is. The minimum clearly comes at the minus 8. Right there. Ah, excuse me, that is not a minimum, that's a maximum. The minimum comes right there at plus 8.
Wait, I'm confused by that.
So, we know the minimum perimeter comes when x equals 8. I keep doing that. You just hate it when you keep making the same mistake over and over and over and you don't learn from your mistake. Okay, so I know something happens at plus or minus 8. And I know that the minimum perimeter occurs at plus 8. Okay? I also know the area is 64. So my rectangle must be a square. If I know that the minimum perimeter comes when one side of the rectangle is 8 and the area of the rectangle is 64, then that has to be 8. So the dimensions of the rectangle with a minimum perimeter are 8 by 8. It's a square.
Uh-huh.
And you will most always find that. In other words, if we had a perimeter and we were trying to maximize the area, we would always come up with a square. Or a circle. In other words, maximum areas are objects that, I don't know how to call it, are like regular polygons. They're either squares, pentagons, hexagrams, circles. They're all same width as length. That maximizes the area given a certain perimeter. Well, this problem's a little backwards in the fact that they want you to minimize the perimeter given a certain area. But actually, we didn't even need the first part. This truly really is not an optimization problem. I mean, it kind of is, but it's the most basic one you can have. There's a bunch of optimization problems that are still easy and a notch different than this. How much time have you guys spent on optimization? I mean, I see a lot of questions over here that are optimization problems.
None.
None? So you haven't really gotten into it yet?
Not really.
Well, then let's take our last 5 minutes and do some more of these problems on the left.
Okay.
Because I don't see any need to get ahead of you. We might as well stay. Let's do 25.
It would be 2x, no, 3x, so no, it would just be x squared minus 9.
And I'm going to set that to 0 to find my critical points. So what's x going to be equal to?
Plus or minus 3.
Okay. Now, you might as well use the new technique that I've taught you to determine whether that's a local maximum or a minimum. In other words, we started with a cubic, so we figure one of these is a local maximum and one of them is a local minimum. We just have to figure out which one. So take the second derivative.
So second derivative would be 2x.
Okay. Is the second derivative positive or negative at minus 3?
That would be
Plug in
positive.
No, plug in minus 3 into the f double prime.
Oh, no, it'd be negative. Sorry.
Okay. So that's negative, which means concave down, which means it's a maximum, a relative maximum. Now let's evaluate the second derivative at plus 3.
Positive
or negative?
Positive.
That means it's concave up, which means it is a minimum. Now, I'm not sure the purpose of their closed interval here, because they don't ask about absolute maximums and minimums. They only ask about local ones. So there is no need to examine the endpoints. If they'd asked us also whether these were absolute maximums or not, we would have had to do more than just figuring out whether it was negative or positive. We would have had to evaluate the original function at minus 3, and again at plus 3, and again at both endpoints. That would have given us 4 values. And we could figure out whether either of the relative minimums or maximums were also absolute minimums or maximums on that interval. And I suspect not, because cubics look like this. Okay? And we found this point to be at plus 3, and we found that point to be at minus 3, even though that's not the way I've drawn it, but nonetheless, you get what I'm saying. In other words, if we go outside and we go from minus 7 to 7, clearly we're going to have points that are less than our local minimum and greater than our local maximum. So if I was examining the absolute maximum and minimum for this function, I would have to figure out what that value was on the y-axis and what that value was on the y-axis. And I would have to compare all 4 values. And then I would know where the absolute maximum and absolute minimum were.
Okay.
Let me just read these directions a little bit better, because no, I'm a little disappointed that they didn't ask that. As long as they're going to include a closed interval, then why wouldn't they ask about absolute maximum and absolute minimum? Because that forces you to do a little bit more work. Actually, a lot of work. If I'm just looking for locals, I didn't need to figure out what the second derivative was. I just needed to figure out whether it was positive or negative. But if I'm trying to determine whether that's an absolute maximum or an absolute minimum, I got to figure out what its value is. In other words, I got to plug in 3 into the original function. And then I got to plug in minus 3 into the original function. And then I got to evaluate all 4 numbers. Oh, and then I got to plug in minus 7 into the original function and also 7 into the original function. I end up with 4 values. Just, I do know that on a closed interval that is differentiable, there has to be an absolute maximum and an absolute minimum. That's one of the theorems. As long as it's a closed interval. If it's an open interval, there doesn't have to be one. In other words, when I have an open interval where I have circles on each end, there is no absolute minimum or maximum. But if I've got closed circles on each end, there's going to be an absolute minimum or maximum on that, as long as it's differentiable over the entire interval.
Okay.
All right. Let's see. We're going to go an extra 10 minutes. Does that work for you?
Sure.
Since we started 10 minutes late, I feel like I'd be shortchanging you if I stopped here. Let's go back and look at 53. Since we got 10 minutes, that's another maximizing problem. Notice the number one thing you want to figure out when you're trying to maximize a problem, in other words, an optimization problem, is whether or not what is your function you're trying to optimize. Well, in these problems here, these are kind of optimization 101 problems because they only give you one function, okay? So our function that we're trying, this is the profit in dollars, right, that he makes depending on how many people are on the bus. So that is the function that we want to optimize, and we want to maximize it. We want to figure out what n gives us a maximum profit. So first of all, let's distribute this, make it a little easier to read. Or, excuse me, make it a little bit easier to take the derivative of. We don't have to use the product rule. Once I distribute it, I have a polynomial and I can just differentiate term by term. So P of n is equal to 50 minus n. That's it. So what gives them a maximum profit if I set that equal to 0?
Just 50.
Exactly. 50 passengers. And they tell us that it holds 100, so we're safe. In other words, we didn't come up with an answer of 102. Although is defined only for positive integers, treated as a continuous function. Okay. How many people should the guide take to maximize the profit? 50. Suppose the bus holds a maximum of 45 people. Now they're talking. How many people should be taken on a tour to maximize the profit?
Would you say minus 45 then? Wait. No.
Let's look at our profit function. That's quadratic. Okay? It's quadratic that opens down because that coefficient is negative. So it's a quadratic that maybe looks like this. Okay? And this n that we figured out was 50. So if the bus only holds, and this has to be pretty much be the picture we're looking at. I mean, it could be lower or higher or left or right. I may not have it in exactly the right spots, but I know it's a parabola that opens down. And the point we just calculated was that. The maximum occurs when n is 50. That's the n scale. That's the profit of n based on n. Well, if I look at that graph and I say the bus can only hold 45 people, I can tell that 45 people is not as big as profit as 50, but it's a bigger profit than 44 people, or 43 people, or 42 people. So 45 would be the answer.
Oh, okay.
Only because I know I'm looking at a quadratic. In other words, I'm not looking at some complicated function. I'm looking at a quadratic that merely has one vertex. And that vertex is an absolute maximum, always. All quadratics, parabolas that point down have an absolute maximum that's the same as that relative maximum. And I can see from the graph that all points left and right are less. But if that's 45 people, and that's the most the bus holds, there's no smaller amount that generates a higher profit here from my curve. I can see that. So the answer would have to be 45. All right. Let's see if they got any other interesting problems here that we can do in a few minutes here. Pull that down just a little bit. Maximizing revenue. Yeah, let's do one of these. Revenue. Do it pretty quick here. The revenue function. They're making these really easy because they're giving you the function that you need to maximize or minimize, and it's only a function of one variable. Where it gets a little more difficult is when it's two variables. What's the rest of that say? Is it 30x or 300x, and is there a number on it?
Here, let me just look in the book.
Yeah.
It's 300x.
That's it?
Mm-hmm.
Again, that's a parabola, like that. So once we find this point here, that's an absolute maximum also. Okay, how are we going to find it? What's r prime of x?
Negative 120 less 300.
So we get x is going to be equal to 330 divided by 12, which is 15/6, which is 5 halves. So when the price of a smoothie is $2.50, we generate the maximum amount of revenue. Now, they told us that for x between 0 and 5, that's correct?
Mm-hmm.
Okay. So that's clearly the number that generates the most revenue, 5 halves, 2.5. That's the critical point of the revenue function.
Mm-hmm.
Determine, now we're getting questions, determine the absolute maximum value of the revenue function and the price that maximizes the revenue.
Would it just be 5 halves?
Yeah, it would be. I mean, these questions are a little silly because they're dealing with all quadratics. It'd be one thing if it was a cubic. If it was a cubic, it would make sense because then we'd be looking at something like this, and it's possible that there could be a point over here still inside the interval that would be a higher maximum than this local maximum. But
Not very
looking at a parabola, that's it, that's it, that's it. There's no endpoints that are going to be higher.
Mm-hmm.
So these aren't really terrific optimization problems, but you'll get to them. They're just kind of leading into it.
Okay, well, cool. Thanks.
Sure thing, Jake. And once again, I'm sorry for being 10 minutes late.
Oh, no, it's fine. Mistakes happen.
I figured out how to read my calendar a little bit better. I'll talk to you next Tuesday at 7.
All right, yeah. I'll see you later.